So in the previous class, we have seen that in case of a helium neon laser, population inversion occurs on several transitions. There are two infrared transitions at two infrared wavelengths and a number of visible transitions at visible wavelengths. They occur for transitions. 3.39 micron is obtained from transition between this we call upper laser level 1, this is upper laser level 2, this is lower laser level 1, this is lower laser level 2. That neon presents multiple lasing transitions occurring from two sets of upper and lower laser levels have been discussed in the previous class. I am not going into detail. So 3.39 micron originate for transition between upper laser level 1 and lower laser level 1. The second infrared light of wavelength 1.15 micron originate for transition between upper laser level 2 and lower laser level 2, while there are a range of visible lights originating transition from upper laser level 1 and lower laser level 2, and they give out light, red light at 632.8 nanometer, orange light at 612 nanometer, yellow at 594 nanometer, and green at 543.5 nanometer. However, transition at 1.5 micron has the highest gain, and therefore it is not surprising that the very first helium neon laser that was operated by Ali Javan and his team at Bell Telephone Laboratories operated on this infrared line because it has the highest gain. So, how then one would make the laser less on transitions and other transitions, in particular the ones which have lower gain, for example, the visible transition. In order to bring any other transition into lasing, selective losses can be introduced to other competing transitions, which is readily doable by proper selection of cavity mirrors. You may wonder, so why can't we use a dispersive element such as a prism inside the cavity? Because prism will, as we know, spatially split these beams and would allow at a time only one of the wavelength to oscillate back and forth inside the cavity. And then tuning this prism or one of the output mirror should be possible by tuning one of the output mirrors of the prism to select any of these wavelengths. However, if you see the factor by which the shortest and longest wavelength differ, that is, shortest one is 6328 micron, and the longest wavelength is 3.39 micron. So there is a factor of almost 5, even more than 5. So by using a single dispersive element, it won't be possible to select wavelengths over such a long range. That is, the shortest one and longest one differs by lambda 2 is more than even 5 into lambda 1. That is why the wavelengths are chosen here, selected here, by selecting the loss, by selectively introducing loss simply by using cavity mirror of appropriate transmission loss. Let me elaborate it a little. You see, suppose this is my wavelength and this is the gain. So first the visible transition, it is let us consider the red line, which of course is the least gain. So this is at 0.6328 micrometer. Then the next one, which is the highest gain, is the infrared transition, which is at 1.15. And then the third transition, the second infrared, which has intermediate gain, which is 3.59 micron. Now suppose the cavity offers same loss on all the same transmission loss on all these wavelengths. That is, transmission loss offered by the cavity is independent of the wavelength, doesn't depend on the wavelength. Therefore, the loss line can be represented by a straight line parallel to the wavelength axis in this gain curve. Suppose the transmission loss of the cavity is such that it is located somewhere and it is parallel to the wavelength axis because it doesn't depend on the wavelength. For all the wavelengths, the loss is same. Now, for such a loss, you can clearly see that there cannot be any amplification of light at red wavelength or at this infrared wavelength because the gain is much less than loss. Loss is so much more than the gain. Therefore, oscillation or amplification of light at this wavelength is not possible. So only this transition with the highest gain will be able to less in this. That is why the Ali Javan and his team, when they invented helium neon laser, they obtained emission at this way. Now, if you have to choose, say another wavelength, for example, say this one, which has the minimum, that is the visible. So what you do, so this is your helium neon active medium. You have created gain, so it is on the verge of emission, and you have placed it inside in a cavity. One of the cavity mirror is 100% reflective, the rear mirror, which is also a bit concave. And then you have the partially transmitting. It offers partial transmission to the light that is growing inside. And suppose it offers, we have designed this cavity inside, this is a dielectric mirror, and so this output mirror or the partially transmitting mirror is a dielectric mirror in which you have coated in such a way that you can provide loss selectively on different wavelengths. Suppose for the line which has the highest gain, that is 1.15 micron transition, that wavelength, suppose this mirror offers 10% reflection at 1.15 micron. And suppose for this transition at 3.359 micron, it offers a reflectivity of say 40% at 3.59. And the transition with lowest gain, it offers much higher reflectivity, say 90%. These are all very qualitative figures. I'm only giving this to make you understand how you can choose different wavelengths by providing losses, selective losses at different wavelengths at 0.6328 micron. So then, the transition, which is the highest gain, 1.15 micron, the light that grows inside this cavity, as it shines onto this mirror, the mirror transmits 90% of this, that is, it is 90% lossy, and it reflects only 10% of this light back, 1.15 micron. For this one, 3.59 micron, it 3.59 micron, it transmits 60%. That means 60% of the light which grows inside the cavity at this wavelength is lost. And for the red light, it transmits only 10%, 0.6328 micron. Only 10% of the light is lost from the cavity and 90% is reflected back. Therefore, for this wavelength, the cavity has the least loss. For this wavelength, the cavity has maximum. Now suppose if we locate the loss lines now in this, so for 1.15 micron, suppose the loss line is located here, loss is very high. For 3.59 micron, loss is, this is the loss line, this is the loss line. Loss line is now wavelength dependent. For this, the loss is so less that it is located here. So now you can see in this scenario, there cannot be any lasing on either of these lines. The line with the highest gain cannot laze because the loss is now more than the gain. Same is true for this line as well. While for the transition, which has the minimum gain, will only be able to. That is because the cavity has been designed in such a way that it selectively introduces more loss in the lines with higher gain and less loss for transition of low gain, thereby allowing oscillation or amplification of light possible at the wavelength for which it has the highest gain, it has the smallest gain. Now in the visible range, as I have already said, the strongest line is the red line, while the orange, yellow and green lines are very weak and understandably have no commercial value. You see, the lower laser levels are energetically located much above the ground, and they actually radiatively relaxes very fast to an intermediate level, which is 3s, which actually is a metastable state. And this energy from this state can relax by collision of the neon atoms in this state with the wall of the tube. So basically what happens, the neon atom, this 3 state, which is the metastable state, the lower laser levels, say as the lasering process continues, the energy as the result of the onset of the lasering process comes down to the lower laser level. And from here, they actually relax very fast to this level. And this is a metastable state. So it actually, neon atom at this state, when it collides with the wall of the tube, neon atom comes down to the ground state. This is the ground state. And this excitation energy is given to the wall. Wall takes the energy. Therefore, to facilitate the relaxation of energy, narrow bore tubes are therefore. If the diameter of the tube is narrow, then the rate of such collision with the wall of the tube will be more, so relaxation of energy will be faster. If this energy relaxes faster, So would be the population which is coming down to the lower laser level as a result of lasing would also very quickly come to the ground state, and therefore would be available to for the continuation of the this lasing process, because once the neon comes to the ground state, it will again collide with helium at the excited states, and the population from the ground state will once again go up to the upper laser level, and the process of lasing will continue. So therefore, you see, the power scaling of the helium neon laser is thus not possible by increasing the cross section of the discharge tube. Okay, let me mention here that how can you, for a gas laser, the power scaling is possible if you have to increase the power of the gas laser. How do you do it? The best way to do it is increase the operating pressure. Because if you increase the operating pressure, you increase the number density of the active species, that is the light emitting species, and if there are more species, you will generate more power. As simple as that. However, in this case, you cannot increase the power by increasing the operating pressure, because if you operate at a higher pressure, you would not be able to obtain flow discharge under continuous operation, because we know that as you increase the pressure, obtaining glow discharge is not possible for continuous discharge. If the discharge has to be sustained continuously with glow, then the operating pressure must be very low. So you cannot increase. You already know the reason, so I am not again elaborating this. So the laser has to be operated at low pressure. You cannot increase the power of the laser by increasing the operating pressure. So what would be the other way that you can increase the number of active molecules by maintaining the same pressure? You increase the volume of the discharge tube. So if suppose the discharge tube originally was this, and you cannot increase the pressure, so you increase the volume of the discharge tube. That you can increase in two ways. Either you increase the diameter of the tube, so you increase the volume, or we increase the length. That is, if this were the original length, increase the length. Now, let us first assume increasing the volume by increasing the diameter. So if you increase the diameter of the tube, you are hindering the relaxation of this metastable state as a result of collision, tube one. Because if the diameter is more, the rate of such collision will be less. So the energy from this metastable state cannot very efficiently relax. So this will not give you, this will not help you scaling up the power. So the only alternative is to increase the length of it. But you cannot increase the length indefinitely. It is limited. You cannot have increase the length to any value and keep on increasing it. So this is the reason why the maximum power that can be obtained from helium neon laser is limited. Commercial lasers are now available in the power range typically between a milliwatt to tens of milliwatt, which is not very high, as you can recognize. And as we have seen, once the neon atoms return to the ground state, they become available for re-excitation and in turn continuation of the CW operation. In contrast, helium, as soon as the helium at the excited state, either here or here, collide with a neon atom in the ground state, it comes down to the ground, while its energy gets transferred to the neon atoms. And once it comes down to the ground state, it is again available to continue this cycle of process of lasing, that is continuation of the continuous operation of the laser. Now, as the operating pressure is low, we just saw that the operating pressure can. The broadening of gain is predominantly Doppler with a full width of about 1.5 gigahertz. Let me elaborate a little. You see, the pressure cannot be increased. So that's why we are saying that the pressure broadening of gain is less. Gain broadening as a result of pressure is low. Why so? Because you see, if an excited atom collide with another atom, then the collision may actually help the excited atom to release its energy, to relax its energy. So that means a collision reduces the lifetime of the excited state. And if the lifetime reduces, that as a result of, as a consequence of Heisenberg uncertainty principle, increases the broadening of the energy level. That is, it results in the broadening of the gain. Therefore, if you increase the operating pressure, you increase the broadening of the gain, which is called pressure broadening. Now, because helium-neon laser operates at very low pressure, its pressure broadening is low. Now, in the discharge tube, you dissipate a large fraction of the pump energy, which is eventually realized as heat. So the temperature increases. And the temperature is often much above the ambient temperature. So at such temperature, high temperature, the gas atoms will have wide range of velocity, and they follow the Maxwell distribution. The velocity has a distribution. This is the velocity. This is the number of molecules. Now, you know that an atom or a molecule, when it travels with a velocity v, the frequency of light that it emits depends on the velocity, which is as a result of the Doppler. I will not go into detail. So if you increase the temperature, the broadening of the gain also increases. And this broadening is called Doppler broadening, which increases with increasing temperature. So here, in case of helium-neon laser, which operates at low pressure, the broadening is predominantly of Doppler nature as a result of temperature, of the gas temperature. Now, the broadening here is, let me give you just, the broadening here, suppose this is the Doppler broadening, and which is about 1.5 gigahertz. So plotted in here, and this is frequency or wavelength. Let us take frequency. So Doppler broadening for helium laser is about 1.5 gigahertz. So 1.5 gigahertz. So how many cavity modes would be able to lace here? You know that for a cavity of length L, the cavity modes, the spacing between two adjacent cavity modes is c by 2l, where c is the velocity of light. This is called free spectral range of the cavity FSR. Now, a helium-neon laser, the typical cavity length lies between a few tens, say about 15 centimeter to 50 centimeter. Let us take the length as 50 centimeter. If you take 50 centimeter as the length, then the free spectral range becomes c by 2l, that is 3 into 10 to the power 8 meter per second, divided by, for 50 centimeter length, it will be 2 into half meter. So this is equal to 3 into 10 to the power 8 hertz. So 300 megahertz. So 300 megahertz is the free spectrum, the spacing between two cavity modes. So there will be numerous cavity modes ranging across this entire range of wavelengths. Now, so the spacing between these cavity modes will be 300 megahertz. And I show a number of and so on, and also in this side. These are the modes which can oscillate back and forth inside the cavity. Here the length is 50 centimeter. You have the helium neon gain medium inside this. So now, how many cavity modes should be able to less? That means how many cavity modes should see the net gain? It will depend on the location of the loss line. Suppose the condition is such that your loss line is the transmission loss of the cavity is such that, say, the loss line is located here. So if the loss line is located here, you can see there are 1 mode, 2, 3, 4, 5 modes, which have gain exceeding loss. This is the loss line. So lasing will be affected on all these 5 modes. This mode also has not any gain because its loss is more than the gain. And so is this mode. It is gain and this is the loss. So the emission of the laser would look somewhat like this. There would be, this is the power and this is frequency. So the line, the mode with higher power also will give higher output. So there will be lasing on all these 5 modes, and so the emission feature of the laser looks somewhat like this. It is a multi-mode laser, and the emission width of the laser is pretty high. So it is not a very highly monochromatic laser. How can you make it more monochromatic? You force oscillation only on single mode. How do you do it? You actually increase the loss of the cavity. So you increase the loss of the cavity. So the loss line goes up. Take it further up. Even if it is here, 1, 2, 3 modes are lasing. Take it even up. Even here, 1 and 2 modes are lasing. Say, let us take it here. This is the loss line. So if this is the loss line, you can see now, this is the lasing window. Lasing window is the length of the intercept, the loss line, with the gain curve. So only over that intercept, lasing can occur, because outside that, the gain will fall below the loss line. So here you see, this is lasing window. Lasing window is less than free spectral range. So only one line, this line, would now have gain exceeding loss. Any other line will have loss more than the gain. So in this case, the emission would be only on this mode, which has net gain. So it will be basically a single longitudinal mode laser, and the emission of the laser will be very narrow emission. So it will be highly monochromatic. So this is how you can make this laser monochromatic. And for any special application such as holography, interferometry, optical clock that requires large coherence length, SLM helium neon lasers are also commercially available. The general application of helium neon laser include its use as a reference beam for the precise alignment of critical components in the construction industry, laser resonator cavity, sewer pipe, etc. You also know that to read digitally encoded barcodes located on products in supermarket, helium neon laser has also been proved very useful as an educational aid in optics laboratory and many research experiments, academic institutes, because it can give very highly monochromatic output. It is very useful to set up optics experiments, particularly experiments, interference experiments. I think I will stop here today.